Okay, here we go. All right, here's how we do this. Set up our chart. Mass, time, half-life, 0, 0. It says if 10 grams decay. So we start with 10, we go to 5, we go to 2.5, we go to 1.25 grams. Okay, I want you to write it down this way. So half, half, half. It's gone through 3 half-lives. The question told us it took 90.6 years to get there. So we need to figure this out. That's your half-life. After one half-life, how much time has passed? That's the definition of a half-life. The time it takes for half the isotope to decay. Not a quarter, not an eighth, half. That's the half-life. And then you would just add the half-life to itself to get to 90.6. So the way we do this, we say, all right, 1, 2, 3. So 90.6 divided by 3 is 30.2. Yes. So again, you have 3 half-lives, so you divide the time by 3, and that gives you your half-life. So this here is 30.2. This is going to be 60.4, but we don't care about that. We only care about this. That's the answer to the question. 30.2 years, and if the Regents was to take it one step further and say what isotope, according to table N, is the unknown isotope, you would look up 30.2, and it's cesium-137, you guys told me? Yep. Very good. So the homework due Monday is the back of that sheet due today. I'm just going to read you the answers. We're not going to go through it slow. We just spent a lot of time doing this. So you should be good. So if you're not good and you're having trouble with the homework due Monday, you need to let me know. You need to come see me. We need practice problems. All right? Okay. All right. A couple more things I want to talk about before we get out. Half-life graph. I just want to get one in our notes. All right, so half-life graph, and it's going to look something like this. We'll put time down here and mass over here. Time in, or grams, mass in grams, let's say time in seconds. But I have a question, and this is on the lab too. Why isn't this a straight line? So if we have a data table, let's say mass and time, and let's say we go from 100 to 50, I'll make up. Let's say it takes 10 seconds. And then 25, 20 seconds. And then 12.5, 30 seconds. And then 6.25, 40 seconds. All right, so let's say this data is what we graphed, right? So here's the time. One half-life is 10 seconds. And then 20, so the half-life is 10 seconds. And every 10 seconds, this mass gets cut in half. If you were to graph this, just like the Penny Lab, it'll have a curve to it. Why is it not a straight, completely indirect relationship? It is indirect. In other words, as time increases, mass decreases. So it's an inverse relationship, but it's not a perfect relationship. It's more of an exponential type thing. Why?
Because the amount being transmutated decreases over time.
Good. So the amount that's being mutated every time is half as much. So if you take half of 100, that's going to be 50. If you take half of 50, that's only 25. You take half of 25, that's 12.5. Half of 12.5, 6.25. So when you are decreasing the mass by a smaller amount every single time, it can't possibly have a linear relationship. What's linear mean in terms of slope? If this looked like this, would it have a constant slope? Yes. If the line is curved, the slope is constantly changing. Change in y over change in x. The reason, exactly what you worded it perfectly. The change from here to here is always going to be bigger than the change from here to here, which is always going to be bigger from here to here. So I don't care what you start with, I don't care what isotope, I don't care what it is, because you're cutting the mass in half every time, your change on the y-axis is going to be smaller and smaller and smaller. Yes, your time is the same, 10 seconds, 10 seconds, 10 seconds. But this mass is getting smaller and smaller, so the difference is getting smaller and smaller. That's why it's a curve. That's really important to me that you understand looking at this. That's why it's a curve. All right, the change in the y is not the same as the change in the x. It's not going to be a linear relationship. Does that make some sense? Good. All right. Last thing with this. Or last thing for today. All right. Radiation in society is what I title it. We know we use radioactivity in nuclear reactions for weapons, for power. We've already talked about it. But we've also talked about, briefly, medicine, right? So radiation in society, primarily medical use, right? It's used in scans to detect. What did I do wrong? What am I doing? Detect diseases or injuries. That's what these scans do. Radioactive tracers is a term. All right. PET scans, PET scans, they use positron emission topography. So those are positrons, PET scans. CT scans also use them. Use radiation. Let's see. I just printed out some stuff here. Targeted alpha therapy, TAT. There's boron neutron capture therapy. Let's see. There's a bunch of this stuff. I mean, I don't need to go over all of it, but put a little star here. Radiation therapy for cancer. Cancer treatment. And obviously I'm running out of time. I do want to show you that carbon dating thing, but I'll have to do that Monday. We'll stop there. Bell's gonna ring in a minute. That's the last part of this unit, is just talk about some uses. There are actually 5 isotopes that could be on the reagents. We'll talk about it on Monday. Don't forget the homework. And that's it. Have a good weekend. If you're not doing anything around 7 o'clock, might as well come